Okay, so I would like to comment again about this very interesting relation that gives us the rate of gene production, mRNA production, gene transcription, as a function of the transcription factor concentration, the free transcription factor concentration. This function here gives us the rate of gene expression depending on the concentration of the regulator. This function here can be seen as a transfer function between the input, which is the transcription factor abundance, and the output, the level of gene expression. The function, the transfer function, this regulatory function also, it's called regulatory function, here is the hyperbolic function, which varies rather continuously when the concentration increases. With a linear behavior at small concentration, a saturation at high A concentration, at end value half, at concentration equal to the dissociation constant. We already discussed of this hyperbolic function when we first saw the equilibrium of the association-dissociation reaction and computed the ratio of the associated compound over the total amount of A. Remember, this was the first dealing with equilibrium and showed that this was A over A plus. This is exactly the computation that brought us to expressing the equilibrium bound promoter concentration that gives us the regulatory function. Okay, so here with this we have as a regulatory function a smoothly varying behavior with the transcription factor concentration that at some point saturates. When you increase concentration of transcription factor, the transcription increases linearly, and for high transcription factor concentration, the transcription is saturated at a maximal rate that will be dependent on some coefficient K2, transcription, the efficiency of transcription. Okay? This is our first case for a regulatory transcription factor corresponding to our model, which was one promoter and transcription factor that could bind, unbind on the promoter. Many cases of gene regulation, rather than such a regular linear monotone increase of the gene activity, rather see for the gene activation some more threshold-like behavior, where the activity of the gene is rather expected to have more a switch-like behavior, meaning that for small concentration of the transcription factor, here would be the rate of mRNA, mRNA transcription dependent on the occupation of the promoter. So rather than having this behavior that was in our model, a single transcription factor molecule binding on the promoter, what is expected in many cases as regulatory function is more a switch-like behavior, where for small concentration there is no or very low activity of the gene, very low transcription, and at some threshold there is some sudden increase of the transcription that rapidly saturates at a maximal level. So a switch-like behavior for concentration of transcription factor smaller than some threshold, no gene activity. For some higher transcription factor concentration, some maximal activity, gene off, gene on. This is what is expected to occur for many genes and proven also to behave so. In other words, we have here a model for the gene regulatory function which is almost linear increase of gene activity, and we will now obtain a model for gene regulatory function where the model is non-linear, meaning that the variation is sudden and not a constant variation over the ranges of concentration, from linear regulatory function to a non-linear regulatory function. I will now show you with the chemical formalism how this switch-like behavior can also be obtained and explained and put into mathematical terms.